Hello? Yes, we're going live. Hello? Hello? Yes, we're going live. Okay. Hello? Okay. Google quote. Google quote. Beep! Google quote. Beep! Let me just call Pom Pom 15. Let me just call Pom Pom 15. Dee. Hello?
Hello, sir. Welcome to Honey. Can I take your order?
Stop! You're being recorded.
And do you want chicken masala?
Stop! You're being recorded. What is going
curry.
on?
You want curry with rice and chicken masala?
What?
Curry, rice, and chicken masala with samosa.
You know a lot of people is listening to you right now.
Are you sure you don't want any chicken masala?
Join my server.
Okay, I will give you 10% discount.
No.
So no chicken masala. I will give you 10% discount.
Come on.
What about samosa?
No. I need you to join my link. Join my link, please.
Curry and rice.
Everything you said gets copied every single second. Everything you said gets copied every single second.
Hello, sir. This is Speedy Walk. How may I help you?
Oh, sorry.
Hello, sir. This is Speedy Walk. How may I help you?
Oh, sorry. It's happening right now.
Hello, welcome to Curry. How may I help you?
It's happening.
You want some chicken masala?
Yeah.
What about biryani?
Do you like South Park? Yeah.
No, this is not Papa. This is Hari Kari owner. You like that?
What
I
is
am
that?
Abdul. I am Abdul.
Nah.
This is Hari Kari owner. I am Camille Habib Papa. What? Camille and Camel. Habib has a corn on the cup. And how may I help you? Don't you want my chicken masala?
Watch your live stream. You're actually being recorded.
Dude, this isn't cool. You can't record someone without their consent. That's actually illegal, you know.
What?
I never agreed to be in your video. I never mean to be recorded, and you're recording me without my consent. Don't you want, like, you know? I'm not trying to act like a Karen or anything, but yeah.
Look, Alan Shields is actually listening to you.
God damn it.
Look, Alan Shields is actually listening to you. Okay.
Just why? Just why are you recording me without my consent?
Okay.
I never agreed to this, and yeah, please leave me alone. I never agreed to this, and yeah, please leave me alone.
Hello? Alan Shields, if you're actually listening right now, please join here. Please. Hello? Alan Shields, if you're actually listening right now, please join here.
I'm gonna go back to playing Minecraft. See you later, dude.
No way! Stop!
What now?
The
I'm gonna want to do
the black hole, the gravitational wave.
Hello, this is Tyrone. What can I get you from KFC?
The gravitational wave. The gravitational wave will hit off and go like, Yoo.
Don't you want some chicken or some French fries?
1 more minute left.
Well, can I get you some Kool-Aid? Okay, so I'm gonna pass it to my.
Oh shoot! Sorry about that.
My game.
Hello.
Oh my God! Hi. Wait. I'm in the show.
Yes.
Where's that thing? Wait. I'm in the show.
Please wait. I'm trying to do something.
Where's that thing? It's been a minute. Now what?
Waiting for the National Science Foundation news.
It's been a minute. This needs to arrive. Wow, nearly said bish. I didn't swear. I said B-I-S-H, not B-I-T-C-H. I didn't swear. Yeah, same. B-I-S-H, not B-I-T-H. I didn't swear. H. Yeah, same.
Did I hear like a doom?
What?
Did I hear like a doom?
Where is that bish? Not swearing. I'm not swearing. I said, where is that bish? No swearing. Kian? Not swearing. I'm not swearing. I said, where is that bish? No swearing. Kian? B-I-S-H. Hey, do you want to play Megaphone Obby with me one day? I'm on stage 230.
I'm sorry, you have to mute.
Okay.
So, I'm sorry, you have
Wait. I can remove myself?
No, you can't, but you have to mute like this.
How do I do that?
Press the mute button.
Mute button? Where is that mute button?
Press the mute button.
Where is that mute button?
Hello? Hello? Hello, please add yourself. This is a misunderstanding. Hello, please add yourself. This is a misunderstanding. Add yourself, please. You don't have much time. It's actually starting at any moment now. You don't have much time. It's actually starting at any moment now. It's been 1 minute and there's nothing happening. It's been 1 minute and there's nothing happening. Please add yourself. Gmail. Please add yourself. Hello? Gmail. Please add yourself. Hello? Here's my stream login code.
Jackson, Director of the Green Bank Observatory, Dr. Tony Beasley, Director of the National Radio Astronomy Observatory, and Dr. Adam.
Do this. I'm scared. It makes me scared. Ah!
But I think she had some problems with her flight and wasn't able to make it. Last, but certainly not least, we welcome Dr. Javier Siemens, Principal Investigator and Co-Director of the Nanograv Physics Frontier Center. And he's brought along with him a significant fraction of the Nanograv collaboration. I think a rather boisterous faction of the collaboration also. Now for a brief introduction to the panelists who are representing the collaboration here today. From left to right on the stage, Dr. Stephen Taylor, Chair of the Nanograv Collaboration, co-lead of the 15-year gravitational wave background paper, and an assistant professor at Vanderbilt University. Dr. Thankful Cromarty, Chair of the Timing Working Group, co-author of the 15-year timing paper, and Einstein postdoctoral fellow at Cornell University.
Wait.
Finally!
Kian?
Kian?
I added you. I'm really sorry. It's something wrong.
Yeah, my profile picture is a dream core eye. Where is that fish? Well, what I mean by where is that fish is where is the gravitational wave? Really?
It's just a conversation. Please wait. Something is wrong.
Kian. Kian!
Distant
Hello.
the cosmos. These objects
Oh!
reveal a rolling, noisy universe.
Kian!
Of gravitational waves. Rolling, noisy universe.
The Earth rotating.
What's that weird noise?
Oh shoot! I can't do it anymore. The cosmic of gravitational waves. Oh shoot! Oh shoot! I'm running out of time. Without astronomy.
Is it a...
Oh shoot! I'm running out of time. Without astronomy.
Supermassive black holes lurk in the heart of new galaxies, and galaxies grow by merging with other galaxies. When that happens, their black holes
Stop with the weird noise!
become more and more massive over time.
Phew. Can you please, like, move your device away from the weird noise source? Hey, Kian, is it okay if you can move your iPad away from the weird sound source? The sound keeps getting weirder and weirder. And yes, my little brother's watching something I absolutely hate. Kian, enable your mic. Kian? Kian! Sorry. Again. Hello?
Gravitational
I'm
wave
right here.
background,
Something is starting
truly
the
a
camera.
harmony of space and time.
Okay.
Nanograv is an
hello?
NSF-funded collaboration.
Oh yeah, I'm so sorry.
Our goal is to solve some of the deepest mysteries of the
I
universe
swear to
studying
God.
gravitational waves produced by these dancing
I'm really
lights.
sorry. It's not even seeming to work.
These
Show
waves
your
are
screen,
9 meters
please.
long and can only be detected
Okay.
by the most extraordinary.
I'm ready.
To measure these giant but subtle ripples in
Stop,
space,
Mike. Don't stop,
Nanograv
Mike.
created a galaxy-sized detector using some of the most incredible objects in the cosmos. Rapidly rotating neutron stars known as millisecond pulsars.
Oh.
Pulsars are the ultra-dense left behind when massive stars reach the end of their lives and explode. These pulsars are also cosmic
Why?
spin extraordinarily
Okay.
fast,
Next to the speaker.
releasing pulses of radio waves with each rotation. Astronomers detect radio telescopes. By
I
monitoring
can't
the radio
stand the weird noise anymore. I just can't.
Nanograv can detect the slightest deviation.
Why
from
can't I set my volume to 0?
these deviations
Okay, I give up.
in space-time.
No way.
This galactic scale detector
Why
is
can't I
called
set my
pulsar
volume
timing array. Nanograv has now observed an array of dozens of pulsars for more than 15 years, and the results are astounding.
Sorry, I
We are
can't show my
finally hearing
screen.
the faint background hum likely coming from in-spiraling pairs of supermassive black holes. With time, astronomers expect to pick out the individual instruments in this cosmic symphony, revealing unique insights
I
into
sent
the
a
evolution of
Discord
galaxies
a link
and
to
the
that
history
live stream
of the
that was in the play.
revealing unique insights
I
into
sent
the
a
evolution
Discord
of galaxies
a link to that live stream that was in the play.
Excellent, excellent. Truly, truly amazing, and great speaker as well. Yeah,
There we
and
go.
narrator. Truly, truly amazing. This achievement was made possible by an extraordinary collaboration involving
There we
and
go.
narrator. Truly, truly amazing.
Okay.
This achievement was made possible by an extraordinary collaboration involving
There we
and
go.
narrator. Truly, truly amazing.
Okay.
This achievement was
Hello, are you here?
extraordinary collaboration involving and narrator. Truly, truly amazing.
Hello, are you think I already felt that. I think I already felt that. Hello? I think I already felt that. There we go.
Well, I'm not sure if.
There we go.
How
There we
about?
go.
Well, wait. What?
There we go.
How
There we
about?
go.
I'm hearing weird noises. I'm hearing weird noises.
I'm right here. I can hear you. Those captains right below.
What was that? Wow! Ow! Wow! What was that? Ow! Wow! Noise.
Hello?
Hi!
What did you say?
Oh shit! It's my pizza. I'm so sorry for swearing.
Those captains right below. Hello? Maybe it's weird. Maybe it's a weird ow ow.
Oh shit! I'm so sorry.
Oh no. Where are you? You're gone. Hello? Maybe it's weird. Maybe it's a weird ow ow. Where are you? Maybe it's oh no. 2023. You're gone. Please join. Come on. 2023. Join. Come on. Please join. Come on. 2023. Join. Come on.
aren't perfect. At a very small level, they will wobble as they rotate, causing the ticks of our clock to arrive slightly early or a little late over time. At a very small level, then the pulses are delayed and distorted as they travel through thousands of light years of gas in the Milky Way. And finally, while we make the best measurements we can here on the Earth, an example of simulated data for one pulsar shown here, these aren't perfect either. So we have to properly calibrate our data and clean out radio interference in our measurements. To make matters more difficult, each Earth to pulsar arm of our detector is unique. And unlike most detectors we build here on the Earth, we can't go to the pulsars to measure or tweak them. Our goal has been to extract the tiny signal from gravitational waves from many different sources of noise in our detector that mask that signal. It's a really challenging problem, as gravitational waves are constantly passing through our detector, and we can't turn the signal off in order to determine how our detector behaves on its own due to only noise. Many of these noise effects can be much stronger than the gravitational wave signal we're investigating, hundreds or even thousands of times stronger. Some of these effects change depending on the radio frequencies we observe at, whereas gravitational waves are the same strength regardless. So that's one of the many ways we can pull the signal out from the noise. We needed to measure precisely when pulses arrived at our telescopes to within 100 nanoseconds or better to be sensitive to gravitational waves. Over many years, we have performed many careful analyses to uncover the sources of noise and learn how the characteristics of our signal differ from the noise sources. The statistically common signal we extract from all of our pulsars has an astronomically small chance to be produced from the individual pulsars alone. As with our previous data set, we have enormous evidence for a signal with common statistical properties. In each pulsar, the signal of a gravitational wave background may appear as a random oscillation over long timescales, but it imprints a unique pattern between pulsars that we can extract from noise. One of the benefits of our technique relies on the fact that our gravitational wave signal has a very special correlation when you analyze the data from different pulsars together. When the correlation between two pulsars is positive, that means the radio pulses are arriving either both early or both late. When the correlation is negative, then the radio pulses will arrive early in one and late in the other. Notice how Einstein's theory of general relativity predicts that the correlation in the time of arrival offsets starts positive when the pulsars are close to each other on the sky, becomes negative, close to 90-degree separation, then goes positive again when the pulsars are on opposite sides of the sky. Analyzing our 15-year data set, we find strong evidence of this correlation pattern, something like a 1 in 1,000 to 1 in 10,000 chance that the correlations would have been produced only from noise, depending on the analyses we perform. We find that these gravitational waves have an incredibly small strength, so small that they cause space-time to change by 1 part in a quadrillion. Next, Dr. Lou Kelly will talk about what sources will cause gravitational waves of these low frequencies and these tiny amplitudes.
Thank you so much, Michael. And as Michael pointed out, the amplitude of these signals is 1 part in a quadrillion. That's 1 part in 1,000,000 billion. This corresponds to a measurement precision of about 100 nanoseconds over the course of our 15 years of data. And now, while this has been an incredibly challenging signal to detect, it's actually booming loud in terms of gravitational waves. But because we're in the early days of measuring this signal, we can't yet confirm what sources are producing the gravitational waves. We believe, however, that they're produced by some of the most rare and most energetic objects in the universe, binary systems of 2 supermassive black holes, also the coolest objects in the universe. We know that these gigantic black holes lie at the centers of large galaxies distributed throughout the universe. While the black holes themselves are only as large in size as a solar system, they have masses as high as billions of suns. Now, as galaxies grow over cosmic time, they merge with other galaxies, and this provides the opportunity for 2 supermassive black holes to come together. For decades, astrophysicists have theorized that binary supermassive black hole systems could then form and produce exactly the types of gravitational wave signals that we're seeing. Despite years of searches using traditional telescopes, no supermassive black hole binary has been fully confirmed, although a handful of very compelling sources have been identified. The signal we're measuring wouldn't be produced by a single black hole binary, but instead by large numbers of supermassive black hole binaries all across the universe. Each of those binaries produces a slightly different frequency or different tone of gravitational waves, which together produce a symphony or a hum that we call a background. Using new theoretical models, we have simulated billions of supermassive black hole binaries, predicted the gravitational waves that they would produce, and compared that to the signals that we're measuring. I want to share with you those results. Here, the vertical axis shows the amplitude of the signal, corresponding to how many binaries are out there and how massive they are. The horizontal axis corresponds to the distribution of gravitational wave frequencies, how many binaries are emitting at different tones. Models appearing towards the right correspond to binaries evolving in isolation, while models showing up towards the left correspond to binaries that are interacting strongly with their host galaxies. Here in orange is the classic simplified model of binaries that expects gravitational wave signals to show very little interactions, binaries evolving in isolation. In blue are new, more comprehensive models of binaries, starting when galaxies merge and evolving all the way down to the small separations at which those black holes can produce detectable gravitational waves. These models include interactions with the gas and stars and the nuclei of each of their host galaxies and produce much broader expectations. Finally, this is what we measure from the NanoGrav 15-year data. And if we zoom in, we can see that the data is consistent
Oh
with both
no,
models.
I think I heard something.
However, there is more overlap with the blue interacting simulations, hinting that perhaps binaries may not be evolving in isolation, and even in the strongly gravitational wave emitting regime are interacting. In either case, the signal that we're measuring is a bit louder than we expected, which means that supermassive black holes would need to form binaries relatively frequently and/or with quite high masses. We cannot yet confirm whether or not supermassive black hole binaries are producing the gravitational wave background. But if it is produced by binaries, then these models offer tantalizing hints about their properties. We'll need to keep taking data, continue to develop new models and methods to find out more. Other kinds of sources have also been proposed as the origin of the gravitational wave background. Nanograv scientists who study the fundamental properties of the universe have shown that our measurements could also be consistent with signs of cosmic inflation, the rapid expansion of the universe soon after the Big Bang. They may even be signs of new, as yet undiscovered, fundamental physics. The way we'll be able to determine if these gravitational waves are coming from binaries or coming from new fundamental physics is by mapping where the gravitational waves are coming from. Just like we can create maps of the night sky using electromagnetic radiation, we can now create maps of the sky using gravitational waves. As our sensitivity continues to improve, we expect to be able to detect whether the gravitational wave background is stronger on one part of the sky than another, whether there are more instruments from one part of the sky or another. We believe that this would be a definitive indicator that supermassive black hole binaries produce the gravitational wave background. If it is binaries, then as our sensitivity continues to improve over the next few years, we'll be able to resolve the structure of that gravitational wave sky and eventually be able to detect individual binaries that are loud enough to resound above the background. This would be a particularly exciting opportunity for multi-messenger astrophysics, in which both gravitational waves and electromagnetic signals can be observed from the same sources. Once this happens and we're able to see and hear these sources at the same time, we would be able to make unprecedented measurements about supermassive black holes and answer fundamental questions about where they come from, how they evolve, and how they interact with the galaxies that they live in. Next, one of our great founders, Dr. Maura McLaughlin, will tell you more about our collaboration.
Okay, well, I think we'll leave it there for today because very shortly we need to get reorganized for the next announcement today, which is about the ice cube neutrino detector at the South Pole.
Was it
So
me or I'm
obviously,
just
we would
feeling a
like to thank you very
vibration?
much, viewers, for being with us this afternoon. Sorry we had a bit of a problem in the chat there with an invader being a bit silly, but I've thrown him out and blocked him, so we won't be seeing him again. Anyway, thank you. If you do have any questions, now is the time to put them in the chat before we close for the afternoon. Or if you want to follow us over to our other live stream on our channel, we'll be going live in about, well, I don't know, about 10 minutes, something like that. So, you know, you can ask the questions there if you like. If you look at our channel, you will see the other live stream for this afternoon listed in the upcoming events. So we hope to see you over there because, you know, unlike the gravitational wave announcement, we don't know what this one's going to be at all. Just to recap then, astronomers have found, with the aid of pulsars, the background gravitational wave hum of the universe, if you like, that's coming from very, very low frequency gravitational waves originating from the mergers of supermassive black holes at the cores of galaxies throughout the history of the universe. And all of those collisions, all the gravitational waves in those collisions have come together to form this sort of background hum, stretching and distorting space-time quite loudly as it happens. So that's the headline for this afternoon. Of course, we're going to talk about this on next Monday's show. So if you like, you can ask any questions there that occur to you before then. Thank you very much for being with you. And if you would like to stick with us on the other stream, we'll be there shortly. And let's see what's been happening at the South Pole with the ice cube neutrino detector. Sounds intriguing. Hope to see you there. So from us, goodbye for the moment then. Say goodbye, Daz.
Checking.
Is your microphone? Your microphone's not working.
Checking the earthquake detector. That's weird.
Okay then, sorry. Take care. See you soon.
Yeah, see you in a bit.
Hope to see you in the next show.
Bye.
Shut up. Bye. Okay then, sorry. Take care. See you soon.
Yeah, see you in a bit.
Hope to see you in the next show.
Bye.
Shut up. Bye.
I got tricked. What is going on? I got tricked. What is going on? What the?
Nanograv is also supported by the Moore Foundation and the Canadian NSERC and CFAR funding agencies. This result would, of course, also not be possible without NSF's significant investments in the Green Bank Telescope, the Arecibo Observatory, and the Very Large Array. The incredible staff at these observatories have worked tirelessly for decades to benefit not only our science case, but many, many others. Thank you. So what's next? Well, this is not at all the end of the story. This is just the end of the beginning. So what's next? Nanograv is already working on our next data set, which will have 17 to 18 years of pulsar timing data. And we expect that the evidence for the gravitational wave background that we have found in this data set to be much stronger in that one. And we're going to become even more sensitive with time as we increase the length of our data set, as we add more pulsars to our array, and most importantly, gain access to bigger and better new radio telescopes with more dedicated nanograv observing time. In addition, we are very proud to be a member of the International Pulsar Timing Array. The IPTA was formed 15 years ago and consists of pulsar timing array collaborations worldwide. Today, groups in Europe, Australia, India, and China have also released results from their most recent gravitational wave analyses. And we all see similar features in our independent data sets, which of course is reassuring and also incredibly exciting. Furthermore, through this collaboration, and partially supported through an NSF ExcelNet Award, we are working with colleagues around the world to combine our current data set with pulsar timing data sets from large radio telescopes in Europe, India, South Africa, and Australia to form an Uber data set that will be much more sensitive than any of the individual data sets alone. We aim to announce results from a gravitational wave analysis of this combined IPTA dataset within the next year or two. We aim to announce results. This analysis will be truly transformative. It should result in a significant detection of this gravitational wave background hum. In this combined IPTA dataset, we may even detect our first individual supermassive black hole binary source, and likely also be able to observe it with electromagnetic telescopes at optical, X-ray, or other wavelengths, truly ringing in the era of multi-messenger nanohertz gravitational wave astronomy. Ultimately, we will produce an incredible map of invisible gravitational waves from gargantuan black holes spread across cosmic time. We will also probe some other exotic and less well understood sources for this background. We are so thrilled that you are joining us on this journey. Thank you. At one time, all we knew about the universe resulted from visible light, light we can see with our eyes. Then when radio and X-ray and gamma ray telescopes came online, we learned so much about the universe that we just couldn't have imagined before, like the radio pulsars that Jocelyn discovered over 50 years ago. Now, we can only dream about what we'll learn with observations in a different part of the gravitational wave spectrum, from the LIGO detections that visionaries like Kip made possible, with continued investment in our science and in large radio telescopes. And we are certainly expecting the unexpected. All we have to do is keep listening. Thank you. And we are certainly
Let's see if I can avoid missing any more scripted lines here. So that concludes the presentation from the Nanograv team. Thank you very much. Wonderful presentation. Before we begin our panel discussion, I'd like to address a question to Dr. Bell Burnell. Are you there, Jocelyn? Before we begin our panel discussion, I'd like to address a question.
Can I be heard?
Yes, we can hear you fine. So Jocelyn, when you discovered the first radio pulsars, did you realize how important these objects would become to the future of astronomy and gravitational physics?
Well, we could see them had great potential because of their timing accuracy. But I guess we weren't thinking in terms of gravitational radiation back in the late 1960s. So their timing accuracy in terms of gravitational radiation.
I see. Thank you. I'd now like to welcome Professor Thorne to the stage, please. Kip, I will. Yep. Okay. I'd now like to the microphone's up here on the stage. Kip, I will. Yep. Okay. Kip, of all the potential future nanograv observations, which type of phenomena is the one most interesting and exciting to you?
Well, I must say that the prospect of seeing can you hear me? The prospect of determining the properties of these supermassive black hole binaries, the largest, the heaviest black holes in the entire universe, is really exciting.
No!
But to me, there's something even more exciting that's on the horizon, perhaps for nanograv, very probably for gravitational wave astronomy generally in the decades to come. And that's to use gravitational waves to probe the birth of the universe. According to everything we know observationally and theoretically, the universe was born in a Big Bang singularity that was governed by the laws of quantum gravity, laws that are not well understood.
Hello.
And That singularity, however,
My microphone
had to
on.
give rise to gravitational waves. The laws of physics demand that that was the case. And whatever form of gravitational waves they gave rise to had to be amplified by the early inflationary expansion of the universe. And so those gravitational waves must carry a mixture of information about the birth of the universe itself, about the laws of quantum gravity that controlled the birth of the universe and the creation of the waves, and about the inflationary expansion of the universe, all convolved together in a complicated way. So to me, the holy grail of this field in the long run is to explore the birth of the universe and extract that information that's carried by the gravitational waves. Now, the conventional wisdom of theoretical physicists says that those gravitational waves are too weak for nanograv to see. But in my 60-year career, 60 years as a physicist, I have seen conventional wisdom fail spectacularly on several occasions. And so I hold out the hope that some of the gravitational waves that nanograv is seeing are primordial gravitational waves from the Big Bang. But even if they're not, I am still tremendously excited by the science that we have heard about today that will come as the data get better, the statistical analysis techniques get better, and as the various detailed properties of these waves are explored. And we learn so much more about the heaviest black holes and black hole binaries in the universe.
Thank you, Kip. Thank you, Kip.
Nanograv.
Thank you, Kip.
Oh my God, Fox.
Nanograv.
Thank you, Kip.
No. Oh my God, Fox.
Nanograv.
No. Oh my God, Fox.
Oh shoot. Oh no. It's too late. It already happened yesterday. Oh shoot. Oh no. It's too late. It already happened yesterday. Oh shoot. Oh no. It's too late. It already happened yesterday. Oh shoot. Oh no. It's too late. It already happened yesterday. Oh shoot.
So hoping that some of the signal really is an echo from the earliest parts of the universe.
Thank you. The next question, can nanograv observations teach us anything about dark matter? Thank you. The next question
Thank you. Yes, I think they definitely could. So in particular, there are models for dark matter like axion or fuzzy dark matter that also have predictions for producing gravitational waves. And they're in one of the nanograv papers, we do place stringent limits on some of these models that are absolutely competitive amongst the most stringent limits that can be placed on things like dark matter in addition to models of the early universe. So I think it's extremely exciting that while in the most mundane case, we're thinking about supermassive black hole binaries, we are also doing this incredibly precise measurements about fundamental physical properties of the universe at the same time.
We are also doing this incredibly. Thank you. The next question would make a good astronomy 101 final exam question. So astronomy professors out there,
My
listen
bad.
up.
I heard it.
You describe gravitational waves as gigantic, very, very tiny, and booming all at the same time. What are you talking about? Very, very tiny and booming.
Yeah, that's a great question. For us in our measurements, the gravitational waves have an extremely long period, very low frequencies. So that means that the wavelengths of the gravitational waves span many, many, many light years. So they're long in that sense. amplitudes of those gravitational waves, how much they're actually changing space-time, are themselves very tiny. We mentioned about 1 part in 1 quadrillion. However, compared to previous models of the expected gravitational wave background, that signal is booming loud compared to what we thought we would see. And so we're very excited that even though they're very, very tiny, the universe is talking to us. Compared to what we thought we would see. And so
thank you for that.
Even though they're
next question. You mentioned that the next step is to combine all the data sets from all of the international group. How will this lead to new constraints in physics beyond the standard model?
Data sets from all the
How will this lead to new constraints in
Yeah, so right now we are working with our international colleagues on what we're calling DR3, or the third data release of the International Pulsar Timing Array. And this data release will be more sensitive than any of the international data sets because it will have more pulsars, it will have more telescopes, it will have more radio frequencies, it will have more observations. And whenever we add more data, we get a much more sensitive pulsar timing array. This process isn't complete yet. So we can't predict, like right now, exactly what boon in sensitivity we're going to see from this combination, but it should be significant. And with every increase in sensitivity, we'll be able to say more things, to discriminate the spectrum, which is basically the power of the gravitational waves versus gravitational wave frequency for different models. That's really what we want to do. We want to be able to look at, like, how bright is this gravitational wave signal across a range of gravitational wave frequencies. And the better we can constrain that spectrum, the better we're going to be able to discriminate supermassive black hole binary origins from more exotic origins. And so this International Pulsar Timing Array data set, which has a very long time span and increased sensitivity, is going to be really, really, really exciting.
Thank you. I have a couple of personal questions I want to ask. Nanograv is a very large and far-flung collaboration. Judging from this gallery, it's a very tight-knit collaboration. What is the glue that holds this collaboration together?
Take a shot at this. And I'll just say, first of all, I'm so grateful to work with everyone in this room and everyone watching online. I think maybe it's not the glue, but the fact that everyone is so respectful of each other and we're all motivated by the same incredible science. I think that's the glue. That's the main thing. We all want the same thing, but we all want to be good collaborators and friends and colleagues. I don't know. Yeah, we're excited about what we do.
Are you okay?
And we're also excited to work with the people that we work with. So it's really an honor. It's a big deal.
Good answer. Thank you. So could you describe other ways in which Nanograv is having an impact beyond the amazing scientific results?
Yeah, there's some science we stumbled into along the way that we had no idea we would find. A few years ago, we were analyzing a data set and found that the accuracy limits we were hitting were testing and stressing models of the solar system. We have to reference everything back to the center of mass of the solar system, which is not a physical point. It's just a center of mass. So we had to update that. We were talking with the people who build these, and we're finding out that we had the greatest demand for this accuracy, needing to know the center of mass of the solar system within 100 meters, like the length of a football field, something like that. So it's extraordinary. We had to inform this, update it along the way, incorporate it into our search analysis. So we were updating the solar system as well as searching for noise in all the pulsars and finding gravitational waves. So it was extraordinary. There's also some fantastic individual pulsar science that we can do that Thankful's an expert on.
Okay, we can move on to another question. This is actually a follow-up question for Kip. How do you think these results will affect the gravitational wave astronomy landscape and discovery space?
Okay.
So There are four different frequency bands in which we expect humans to be seeing gravitational waves by something like the late 2030s. The high frequency band where LIGO first discovered gravitational waves, where there are now several different detectors around the world operating. That's what the gravitational waves have periods of a fraction of a second, something like typically 100th of a second. Then there is a frequency band where several space-based detectors are likely to operate in the 2030s and beyond. LISA is the most famous of these. That's with periods that are a few minutes to hours. There is the band that we are talking about today with periods of years that Nanograv is operating in, and also the other collaborations elsewhere in the world. And then there is the extremely low frequency band of periods of millions of years. Now that's rather long compared to a graduate student lifetime. So graduate students don't sit there and analyze data and watch the waves come in. Whether you look for patterns of polarization of cosmic microwave background on the sky that are put onto the microwave background by the gravity waves. So patterns on the sky. And so we have these four different bands. And when we can, by the middle of this century, when we have all four bands in operation, this is going to be tremendously exciting. And the science that's going to come out is really, I think, going to be phenomenal. It's like going from Galileo's first pointing telescope at the sky and seeing the four moons of Jupiter to modern electromagnetic astronomy. This is the beginning of that process for gravitational wave astronomy.
Thank you. Do we have time for one final question? Yeah. And the last question then is, how do we know that this won't be a bicep 2-like result?
So, of course, this is something that we have thought very long and very hard about. We do not want to be another bicep 2. And for those folks at home, this was an experiment that announced a big discovery and it ended up not being real. And so we of course do not want to be in that position. We are very confident that we are not going to go down that path. The first reason for that is that in our last data set even, we saw a very, very strong source of common noise among all the pulsars in our array. We couldn't yet see these very special spatial correlations, but we see a very strong source of noise that can't be ascribed to any other source. So even a few years ago, we were pretty sure that we had gravitational waves in our data set. There was basically nothing else that could really create that signal. On top of that, this same source of common noise was seen in the data sets in all of our international collaborators. So they all saw this exact same, consistent source of common noise. Now we have these spatial correlations. The spatial correlations, by chance, in just our data set, are significant at a 1 in 1,000, 1 in 10,000, random chance level, which is pretty darn good. And similar signals are seen in data from a combined European-Indian pulsar timing array analysis, a Chinese pulsar timing array analysis, and an Australian pulsar timing array analysis at different levels of significance, but they're all similar. So this makes it extremely unlikely that this is just some random fluke in our data. We are very confident.
Okay, yes.
Thank you again, panel. I'd like now to ask Sean to provide us with some closing remarks.
Thank you, Michael. Let's give this panel a round of applause. Yeah, keep it going. Yeah. And that's for you in the room as well and all the collaborators that are online. Thank you so much. This is phenomenal. And to quote one of our panelists, this is cool. So thank you to all of our speakers for this report. And I want to also thank the organizers for this event, for this celebration. And I want to thank Michael for his stewardship for today's event and for the Nanograv Physics Frontier Center, but also our co-director here at the National Science Foundation, Dr. Kathy McLeod, Wave, for all of your tireless and hard work as well as co-director for the Physics Frontier Center and for Nanograv in particular. You're welcome. On behalf of the National Science Foundation, I'd like to congratulate the entire Nanograv team on the publication of this hard-earned result. The Physics Division, the Division of Astronomical Sciences, and the Directorate of Mathematical and Physical Sciences are pleased to support foundational research at the frontiers of physical science and are delighted to advance explorations into the wonders of the universe. And we don't do this alone. As mentioned, the Partnerships in International Research and Education, PIRE, NSF ExcelNet, and external agencies and foundations have all contributed to these Nanograv advances. Now, I'm looking forward to future results, holding you to that, in this important new field of low-frequency gravitational wave astronomy and what it will teach us about the evolution of our universe. And of course, I look forward to hearing more music from the Cosmic Symphony. Thank you, everyone. Congratulations. Right. Fantastic. Yep. Great job. Great job.
Support daily head health with Proactive Health from Excedrin, a new drug-free supplement.
Framework to advance new areas of biological research. So I'd like to turn the floor over to Brent Miller, the bioscience advisor, who will give an overview of the framework. Brent.
Thanks, Mike. Good morning, everybody. I'm Brent Miller. I'm science advisor in the Office of the Assistant Director. With the increased interest in partnerships coming from the Office of the Director, Bio has asked me to begin laying the foundation for a partnership strategy framework, and that is clarifying answers to questions like, with whom do we partner, how are those partnerships started, and what do we hope to accomplish with those partnerships. Today, I'm going to describe to you how our initial discussions in Bio are starting to answer these questions.
I didn't even think about that. That's fun.
I'll keep going. I don't think that was a question. All right. This introduction will be followed by some excellent examples of existing partnerships. And these together, it's our intent to provide you with our perspective on what partnerships should be and specific examples, all to engage you to help us think deeper about partnerships in Bio. I'll start off with a high-level topic that's on all of our minds, and that is explaining how we're thinking about partnerships benefiting discovery and translation across Bio. We believe that discovery and translation can benefit from partnerships. On the left, which represents our division leadership. One second. I'm just going to hit later as Simon suggested. Perfect. Great guidance. So we believe that discovery and translation can benefit from partnerships. On the left, we imagine partnerships that will allow us to make new discoveries. Consider partnerships that provide access to infrastructure or new ideas or support research to better understand fundamental biology across bio's discipline spaces. As well, on the right, we envision partnerships that allow NSF to more quickly address, as the director states, the world's largest and most difficult challenges. Think climate change, or addressing the missing millions, or tackling challenges in the next generation biotechnology and/or our use of data. Our intent with partnerships is to have an impact. And to do so, this means balancing our available human resources to build partnerships with all of the potential partners that are out there. So with all of that potential, an overarching principle in our discussions has been that we prioritize partnerships that help address strategic areas of need within bio's discipline space. The slides do advance. The director has encouraged us to use our imaginations with respect to the kinds of partners we collaborate with. Essentially, there are few limits on our considerations, but a clear criteria we must consider is shared interest in advancing fundamental science, translation, and promoting broader impacts. That is, working with like-minded partners. This is really a must. The kinds of partners are listed on the left on the slide. I'll go through those quickly. Bio is really good at partnering with sister agencies across the federal government. We're good at that. We're piloting new ways of partnering with industry. I'm going to tell you a little bit more about that in a moment, but more creative thinking here could be useful for Bio. Bio has a history of partnering with nonprofit organizations, for example, the Bill and Melinda Gates Foundation, or more recently, the Simons Foundation. And these have worked because we focused on shared interest and created mutually beneficial collaborations. But again, creative thinking on your part could help us. And finally, international organizations covering government, industry, and nonprofit organizations. This isn't new territory for Bio. There is a wealth of opportunity here, and many of the current challenges we face are global in nature and require global considerations and responses. So again, creative thinking here could be useful. Beyond advancing science, translation, and broader impact interests, what practical aspects are we looking for in our partnerships? And that's on the right. Our expectations are listed, and each item in the list represents potential gaps, where if filled by partnering organizations, could multiply our capacity to discover and innovate at speed and scale. This bulleted list is really a summary of where senior leadership discussions have focused so far. That is, the shared values for what we expect from our partnership activities and how we work internally. And I'll walk through each of these with a brief explanation. So first, we're looking for clear goals and objectives. For each partnership, we want to document the desired goals for Bio and establish measurable targets to reach those goals. Our primary driver is advancing the science. We want to establish partnerships that provide resources or allow Bio to overcome barriers to advancing our science and broader impacts. We want to be proactive. We want to be proactive in our pursuit of partners. We intend to seek out partners who shared values and interests and design those partnerships to be mutually beneficial.
Oh no, what is going on?
We also expect the coordination for all of this to happen in OAD and the discovery to be in the divisions. The OAD, the Office of the Assistant Director, will provide an environment that promotes organization and open communication, while at the same time providing the freedom to be creative within the divisions, because the divisions know the science and the needs, so they're best positioned to seek out new relationships and potential impact. Next, we'll have open communication and clear guardrails. We know it's not possible to pursue all partnerships. And so the OAD, in collaboration with the division leadership, will clearly state our capabilities, limits, and priorities, both internally and externally, and will strive to preemptively understand our prospective partners' capabilities, limits, and priorities. And all of this is with the intent of creating a process that is efficient and prioritizes impact. And of course, we want to be flexible. We don't know what the future looks like with respect to the kinds of partners or the collaborative mechanisms we may use with them. So we've included this value to being open to new ways of thinking and doing. And finally, we want to track our success through evaluation and metrics. And so more and more, we're being asked by our leadership, Congress, and the executive branch to show progress and impact. So evaluation metrics that are geared towards understanding each partnership's goals.
What? What?
This is the Discovery.
What? No way. I can't believe I got... Where's the black hole so I can expect it? Huh. No. I made something so wrong. Why? It's 2023. Oh. Just like I missed solar eclipse when I was sick. Please wait.
After that. After that.
No, not true. Okay. This is it. I made a very huge mistake. Bye-bye. No.